an introduction to acids and bases topic of this lesson. And it's the first lesson in a whole chapter on acids and bases. And we'll give you an introduction, we'll give you some definitions, we'll talk about strong acid bases and salts and how they can act as acid bases. And then in the next lesson, we'll get to pH calculations and the pH scale. And then finally, we'll finish this chapter off with a lesson on buffers and titrations. Now, this lesson's part of my high school chemistry playlist. I'm releasing these lessons weekly, so if you want to be notified every time I post one, subscribe to the channel and click the bell notification. All right, so let's talk about acids and bases, and we're going to get into definitions. And before we do that, though, you should know that I just got finished recording this and the next lesson with no sound. I forgot to turn on my microphone. It was fantastic. So it turns out I was doing some filming for a different class before this, and then I swapped out the batteries and just forgot to turn it on, and so I just wasted an hour of time. So, however, that does mean that you get rendition number 2, which usually means it's a little better. So I guess maybe that's to your benefit. All right, so talking about acids and bases, we got a couple of different definitions. We got some properties you should know, and we'll start with those properties. So acid, if you notice I've written the title acid here in red and base in blue, and I've done that for a reason. So common way in laboratories to distinguish between an acid base or to check to see if a solution is acidic or basic is what we call litmus paper. And litmus is a color changing indicator. And when you pour an acid on it, it turns red. And when you pour a base on it, it turns blue. And so forever since then, acids are associated with the color red and bases with the color blue. And if you look at my study guide, all of it is color coded in such fashion, acids with red and bases with blue for that reason. So first thing you should file away is that acids turn litmus red and bases turn litmus blue. Second thing you should know is that acids are sour to taste and you shouldn't taste them. And bases are bitter to taste and you shouldn't taste any acids or bases you're using in a lab. Also, you should know that bases tend to be slippery. So, and I say that, but you also shouldn't be touching any bases you deal with in your lab, or acids for that matter. They're very caustic. They will burn your skin and things of this sort. And, I say that they're sour and bitter and stuff like this because you're also going to encounter them in your food, right? Like Coca-Cola has got citric acid in it, and it's got a pH of like 2.5 or so, and things of this sort, of a fairly acidic solution. Vinegar has acetic acid in it, and you put vinegar in your food, or things are pickled with it sometimes and stuff like that. So you are likely to encounter acids and bases in everyday life and other places, but in the laboratory, don't taste them, don't touch them, so on and so forth. All right, so a couple different definitions for acids and bases. Mr. Arrhenius came up with a definition, and then Mr. Bronsted and Mr. Lowry came up with a definition. For the Arrhenius definition, so it's a little bit of a limited definition. It's kind of the first definition. Pretty broad application, truth be told, but it's a little limited for Bronsted-Lowry's taste, and so they came up with a little bit better definition. But Arrhenius said that a Bronsted-Lowry acid is one that, well, let's get this right, is an H plus donor in water. H plus donor in water. So what in the world does that mean? Well, let's take a look. So common acid, most famous acid of all time is not LSD, contrary to what some people think. It is HCl. HCl is your common pool acid. It is also your stomach acid. So, and commonly one you'll find in a high school or college freshman chemistry lab. So really common acid here, HCl. And in this case, if you put it in water, it will give away an H plus ion to the water, forming H3O plus and Cl minus. And so as a result of donating H plus in water, it turns out another way to look at it is it increases the concentration of this H3O plus, which we call the hydronium ion. And so anything that increases the concentration of H3O plus in water could also be looked at as Arrhenius' definition. So whether you want to call it an H plus donor in water or anything that increases the concentration of hydronium in water, there you go. Let's talk a little bit more about that hydronium for just a second, because some people will leave the water out of this equation and just go straight to saying H plus Cl minus. And they'll look at it this way. And the problem, though, is that H plus is super, super reactive. And so the fact that, if this HCl does dissociate in water, the likelihood of any H plus just sitting there in the water, it's not very likely. It's actually going to start combining with water molecules. And so instead of, just showing what we call naked protons or free protons in solution, we show that they actually do combine with water to form this H3O plus. Notice that's the combination of H2O and this H plus right here. So that's kind of the deal there. The other thing you should know is, notice I called this a free proton or a naked proton. So if you look at hydrogen, atomic number 1, and normal isotope of hydrogen, their standard isotope of hydrogen is hydrogen 1. And so it has 1 proton, no neutrons, and then 1 electron. So 1 proton, 1 electron. But H plus, the only reason it's positively charged is because you lost the electron. And so H plus, all it is a proton. And so oftentimes you'll see that's just commonly referred to as a proton, hence my calling it a naked or free proton, or things of that sort. So another way to look at this then is an Arrhenius acid. We could say it's an H plus donor in water, but a lot of people, when they read this and they get accustomed to chemistry, they just look at that and they say, oh, a proton donor in water. So you hear that terminology used a fair amount here as well. Cool. Now, one thing you should note, so this is the hydrogen ion, or proton. This is hydronium. And so the idea is that, historically, we really looked at it as hydrogen ion concentration in water and stuff like this. So, but now we know that actually it combines with water molecules, and so H3O plus is a little better representation of that. The truth is, though, is that each H plus is probably interacting with 2 or 3 water molecules at a time, and so even writing H3O plus is not 100% accurate. So, however, you're going to treat these as synonymous. And in any acid-base textbook and any lecturer is commonly going to, and somewhere in the, at some point, use both. And whether we write H plus or H3O plus, hydrogen ion or hydronium ion, treat them as completely synonymous for the purpose of this chapter. All right, so there's our Arrhenius acid. Our Arrhenius base, on the other hand, is something that is an OH minus donor in water. So something that's going to donate hydroxide ions. And so in this case, common base, most famous one is sodium hydroxide, and it just simply dissociates in water to give Na plus and OH minus. And the key is that it's forming some hydroxide. That's what you need to be a base. And another way to look at this is it increases the concentration of hydroxide. And one thing you should know, I got these lovely brackets here. And these are not parentheses, these are the hard brackets, the nice square brackets. And these brackets are used to mean molar concentration of, so molarity of. And so when I write H3O plus in brackets, you should read that as it increases the molarity of H3O plus. So brackets with hydroxide here, this means increases the molarity or molar concentration of hydroxide ions. So a little more terminology there as well. All right, so that was Arrhenius' definition. And if you look at a typical Arrhenius acid-base reaction like HCl with NaOH here, you'll see a common pattern develop. The H plus and the OH minus combine to form water, and then Na plus and Cl minus form an ionic compound, and any ionic compound can be called a salt. And so that's a common pattern here. So for an Arrhenius acid and base, they react to form water and a salt. And that's pretty much going to be true for any Arrhenius acid-base reaction you look at. Now, our other definition is going to be the Bronsted definition, and we'll find out that, these could actually also be qualified as Bronsted-Lowry acid bases. Turn out every acid or base that satisfies Arrhenius' definition will also satisfy Bronsted's definition. Okay. However, there are going to be some Bronsted-Lowry acid bases that aren't going to satisfy Arrhenius' definition. So this is actually a more inclusive definition, a broader definition. All right. And so whereas any Arrhenius acid-base reaction will form water and a salt, so there are some Bronsted-Lowry acid-base reactions that won't form any water whatsoever. So if you see a question, all acid-base reactions form water and a salt. Well, it's not technically true. You should also realize that we often refer to an acid-base reaction as a neutralization. We brought this up several chapters back earlier in the course if you've been following along with me. But this is an acid-base neutralization. And again, do all acid-base neutralizations form water and a salt? No, just the Arrhenius ones. All right, so if we look at Bronsted-Lowry's definition, they said, instead of looking at H plus donor, OH minus acceptor, they were familiar with a lot of bases that didn't have any OH in their formula like NaOH does. And so they said, we don't really like this definition. So they went ahead and said, well, your definition for acid is okay, but it's got one problem as well. So Arrhenius only looked at acid-base reactions in water, in aqueous solution. Whereas it turns out you can do acid-base reactions in any solvent. You can even do them in the gas phase with no solvent whatsoever. And so their definition was limited to, or Arrhenius was limited to water, whereas Bronsted and Lowry came along and said, just H plus donor, done. So cool. And they also said, and instead of looking at somebody who's giving a hydroxide to the solution, so it's actually just follow the H plus. And if somebody's donating the H plus, well, then somebody has to be receiving it or accepting it. And so they referred to it as an H plus or proton acceptor for the base. Instead, they just said follow the H plus. And so if we look at this reaction between HCl and NaOH here, so HCl is giving away the H plus to the OH, forming water. So by that definition, HCl is the H plus donor in the acid. Hydroxide is accepting the H plus and is the base. And that's kind of the way they looked at it. So that's Bronsted-Lowry's definition. If we take a look at one more Bronsted-Lowry reaction though, so HCl plus NH3, so there's one we're going to look at here. And for a typical Bronsted-Lowry, if you're looking at a Bronsted-Lowry acid-base reaction, oftentimes they'll define it with this lovely double arrow. This double arrow here is what we call the equilibrium arrow. And what that usually is referring to is that we've got what's called a dynamic equilibrium, where a reaction is actually happening in both directions in your beaker at the same time. And there's this equilibrium where it's just happening in both directions at the same rate, but both are happening at the same time. As a result, when we look at Bronsted-Lowry's definition of acid and base, you can actually look at the forward and the reverse direction and get multiple acids, one from each side, and multiple bases, one from each side. So if we look at the reactants first and say, well, who gave away the H plus? Well, HCl did, because he had an H and now he doesn't. So whoever gives away not just an H, but notice it's an H plus. So he was neutral, now he's negative because he lost not only an H, but a plus charge. And so in that sense, we could identify HCl as the acid. Well, who accepted the H plus? Well, ammonia received it here, NH3, because he turned into NH4. Notice he gained an H and he gained a plus charge, so we'd call him the base. But then you could look at the reverse reaction, and if we look at this reverse reaction here, so going backwards, who gives away the H? Well, in this case, it's the ammonium ion, so we'll call him the acid. And who accepts the H? Well, chloride gains it in becoming HCl, so we'll call him the base. And so if you look at this pattern emerge, so when you have a Bronsted acid give away his H plus, he turns into what we call his conjugate base. And that's why I saved a little room here. And when you have a Bronsted base accepting an H plus, he turns into his conjugate acid. And it's common for us to talk about in Bronsted-Lowry terms conjugate acid, conjugate base pairs. And so in this case, HCl and Cl minus form one conjugate acid, conjugate base pair, and NH3 and NH4 plus also form a conjugate acid, conjugate base pair. And so whether you say acid and conjugate base or base and conjugate acid, that's totally acceptable. And oftentimes what you'll find is that, you know, there's going to be a difference in charge here, and whichever one is neutral will probably be labeled as just the acid or the base. Or sometimes it'll just be whichever's on the reactant side will be labeled as just the acid or just the base. But the truth is, you could actually just say conjugate acid, conjugate base, conjugate acid, and just label everything as a conjugate. And that's totally acceptable as well. All right, one other thing you should know here in these conjugate acid, conjugate base pairs, so is that generally the stronger an acid is, the weaker its conjugate base is going to be. So if HCl here is a stronger acid than some other acid, well, that's going to mean his conjugate base ends up weaker than the other one's conjugate base. So let's take a look at this for a second. So turns out we're going to compare HCl to something like HF a little later. So in this case, HCl, HF, if you want to find their conjugate bases, what you want to have them do is just act as an acid. So have them donate their H+. What would they look like after they donate H+? Well, we'd end up with Cl- and F-. Well, it just so turns out, I'm going to tell you that if you had to pick which of these two is the better acid, or the stronger acid, I should say, HCl wins. So it turns out HF is more deadly, but that's for a different reason. So, but HCl is the stronger acid. He's better at dissociating, it turns out, and donating his H+. We'll talk about what a strong acid is here in a little bit. Well, if you had to then rank these two as bases, you're going to find out that F- is a stronger base. And so there's this relationship with conjugate acid-base pairs that if you're comparing two acids, whichever one is stronger ends up with the weaker conjugate base. Whichever one is weaker ends up with the stronger conjugate base. So there's this inverse relationship, and I'll allude back to it later. And this will make a little more sense in a little bit when we start talking about strong acids and bases. All right, so I want to bring up a word called amphiprotic, and you might notice the prefix on here is amphi, like an amphibian. So an amphibian is an animal that can live on either land or in the water. So either one, and well, amphiprotic is one that can be a proton donor or a proton acceptor. It can act as either a Bronsted-Lowry acid or a Bronsted-Lowry base. So give you an example. We'll give you water. So water actually can act as an acid or a base. So in this case, if I have water act as an acid, if he gives away an H plus ion, well then his conjugate base would be hydroxide. However, if instead of having water act as an acid, what if I have water act as a base and accept an H plus? Well, if we add an H plus to that formula, you gain an H and you gain a plus charge, and you get H3O plus. And so as a result, water is amphiprotic. Now, one of the common questions you might get in a section like this is identify the conjugate acid or conjugate base of some species. Like if I said, give me the conjugate base of HCl. Well, I would only ask you for the conjugate base of HCl because he's only an acid. However, in like water's case, it's a more challenging question because I could ask you for the conjugate base, so I'll label as CB, or I could ask you for the conjugate acid, because water has the ability to act as an acid or a base, and that's what makes it tricky. And so you've got to realize what they're asking for. So again, if I ask you for the conjugate base of water, well then you must realize that then water must be the acid. And what do acids do? They give away H plus, and if you get rid of an H plus, you'll be left with OH minus. But if I say, what's the conjugate acid of water? Well, if I'm asking you for the conjugate acid of water, then water must itself be the base. What do bases do? Well, they accept H plus. And if we add an H plus to the formula, we get H3O plus. And so you got to know those definitions of conjugate acid, conjugate base, and how you find them from a formula very well, because that's just a common, lovely multiple choice question from this section. All right, let's talk about strong acids and bases. All right, so strong acids and bases. I've got a couple of lists on your study guide for you. So you got 7 strong acids you're responsible for, and 1 or 2 more strong bases, depending on whose list you're looking at here. So cool, these are your strong acids or bases, and the reason we call them strong is that they are strong electrolytes. You might recall from several chapters back, we talked about strong electrolytes dissociate into ions 100% completely in water. That's what a strong electrolyte is. And so these acids right here, they dissociate to donate protons 100% in water. And so we saw this with HCl, right? So we had HCl in water dissociating 100% to give H3O plus Cl minus. That's what it means to be a strong acid, 100%. Now here's the deal. I'm going to give you the truth. Most people aren't going to tell you the truth. So it's not 100%. It's only 99.9999999%. Okay. So I'm being facetious, but I'm being serious though. It's not exactly 100%, it turns out. But it's just close. For all 7 of these, I mean like 99.999% versus 99.999%, who cares? So they're all virtually 100% dissociation, and we round up. Cool. So that's what that refers to. Same thing with the strong bases. So sodium hydroxide, again, one of the more famous strong bases, dissociates 100% into ions. So that's what we mean. Now, if we contrast that with what we call a weak acid, and again, we said that HF was weaker than HCl, and in this case, it's actually not on the strong acid list. And it's proper, oftentimes, to write it with this kind of equilibrium arrow as a result. Now, the truth is, this equilibrium arrow, you could write this here as well for a strong acid in water. Nothing wrong with that. But you'll commonly see them use the single arrow to kind of show you that, oh, he's strong, by the way, he goes to completion. But for a weak acid, it's proper to show this equilibrium arrow instead. All right, so strong acid 100%. Typical weak acid, they vary. There's a whole host of them. Where there's only 7 strong acid, there are dozens and dozens and dozens and dozens of different weak acids. You don't have to memorize them. If the formula starts with an H and it's not one of these 7, then it's a weak acid. And so it makes it easy to identify those weak acids, assuming you've already memorized these, which means I'm telling you, you have to memorize these. You're on the hook for knowing who the strong acids are and who the strong bases are. Cool, so if you memorize those 7 strong acids, and then you see another acid beginning with an H that's not on that list, you know by default it's weak. And a typical weak acid is going to dissociate less than 5%. So, and oftentimes it's like significantly less than 5%. Like 0.01% is not unusual for a weak acid. All right, so your strong bases, if you notice, these all have hydroxide. They're all ionic hydroxides. They're metal hydroxides. So if you have like a organic with a compound with an OH in it, it's not a hydroxide. If it's organic, it's carbon-based, and and it's just non-metal with OH, and that's not an ionic bond, so you don't have to have a negative charge. But if it's a metal hydroxide, specifically with one of the group 1 metals, lithium, sodium, potassium, rubidium, cesium, or one of the group 2 metal hydroxides, that's your strong bases. Now, if it's a transition metal hydroxide, not going to be a strong base. So it's not all metal hydroxides, just the group 1 and group 2 metal hydroxides. One other quick thing to note, magnesium hydroxide. So it's on some people's list, it's not on other people's list. So it turns out that these group 2 metal hydroxides, whether or not you count them as a strong base depends on how you define it. And when the chemists defined it, they said for the amount that does dissolve in water, it dissociates completely. Well, it turns out these actually just aren't that soluble in water. And they get more soluble as they get bigger down the periodic table. And so magnesium hydroxide specifically has such a low solubility in water that a lot of people actually don't put it on their strong base list. So, however, these all have really high solubilities, and there's no argument about them being strong bases. So, but like barium and strontium hydroxide, like maybe up to 0.1 molar, calcium hydroxide 0.01 molar, magnesium hydroxide something lower than that. But they still get counted as strong bases. And so this is one of those places where we just kind of like oversimplify things just a little bit because teaching you the truth would suck. And so if you're dealing with these in the lab, you'd have to deal with some solubility issues. But on paper, you're just going to treat all of these. They're all strong bases. They all dissociate 100%. Done. All right. One other thing you should note, H2SO4 here has got 2 H's. So notice all the rest of these strong acids, the other 6, they all have just 1 H plus ion to donate. We call them monoprotic, 1 proton to donate. Whereas H2SO4 is an example of what we call polyprotic, many protons to donate. Specifically, we could call it diprotic, 2 protons to donate. What you should know, though, is that it's only the first one that is a strong acid. And so if we put H2SO4 in water, the first H dissociates completely. So you're going to get some H3O plus and then HSO4 minus. And that reaction is going to go to completion. On the other hand, though, if you take a look at that HSO4 minus, further reacting with more water, it's only going to associate to a small extent because he's just a weak acid. He's not one of our 7 strong acids. And so you're only going to get a tiny bit more H3O plus as a result. Cool. Contrast that with magnesium, calcium, strontium, and barium hydroxide, all of which have 2 OHs. When they dissociate, they're all going to actually donate both OHs into solution. And so we talked about Arrhenius said, acids donate H pluses, bases donate OH minuses. That's why we're focusing on this. And we have to remember that H2SO4, the only diprotic strong acid, only the first one's going to dissociate completely. But all these lovely metal hydroxides, group 2 metal hydroxides, they all dissociate both OHs. So if I give you barium hydroxide here, you're going to know that it dissociates 100% to give you twice as many hydroxide ion. And that's going to be important when we start doing pH calculations in the next lesson. Now, if you found this lesson helpful, would you consider giving me a like and a share? One of the more helpful things you can do to help other eyes find this video. If you're looking for the study guide that goes with this lesson, if you're looking for practice problems on this, check out my premium course on chadsprep.com. A free trial is available.